Hey guys, so in our second video today we are going to be talking about potential energy diagrams, and we are going to have to know how to read these and how to interpret these for this unit. So number one, what is a potential energy diagram? Well, it's a graph that basically plots the heat of a reaction during the course of the reaction. So it's showing you what's happening to the energy throughout a chemical reaction. Now again, this is when the reactants, the bonds are breaking, and then new bonds are forming to form the products. So we'll take a look at that here on these next slides. So there are two different kinds of reactions. There's endothermic and exothermic, and we have to know the difference between the two. So in an endothermic process, the potential energy of products is more because energy is gained. So basically energy has to be put into the system in order to break bonds. In an exothermic process, the potential energy of products is less because the energy is lost. So the change in energy is going to be less in an exothermic. The energy is released, and this is when the bonds are being formed. So here is a picture of a potential energy diagram, and we're going to go over what each of these things are here in just a second. But the activation energy, also denoted as EA, is the energy level that the reactant molecules must overcome before a reaction can occur. And remember, when we talked about those factors that can influence the rate of reaction, the activation energy can be lowered if we add a catalyst, okay? So here on the screen, we have our energy diagram, right? So on our y-axis, we have our potential energy. Typically, this will be in joules or kilojoules, some kind of energy measurement. And then on our x-axis, we have our reaction pathway. So this is basically just saying this is the reaction that's taking place. Over time, this is what's happening. The activation energy is the difference between the energy of the reactants and this thing called the activated complex. Okay, this is kind of the in-between of what's going on as our products are being formed. So our reactants are on the left. This is what goes into the reaction. The activation energy is the amount of energy that it takes to get, basically to get the reaction going. So it's going to be the energy from here where we have our reactants up to our activated complex. And then our products, of course, will be on the right. And the delta H, this is the change in the enthalpy. And this is going to tell us whether or not our reaction is endothermic or exothermic. Now you can see here that this particular reaction is already labeled for us. It is endothermic. And this is because the energy of the products is greater than the energy of the reactants. Because remember, our energy is plotted right here on this y-axis. So if you're taking a look at one of these potential energy diagrams, we can tell whether it's endothermic or exothermic based on the energy of the products compared to the energy of the reactants. So here, because the energy of the products is higher, that means our delta H is going to be positive, which means this is going to be endothermic. And again, here is an example of adding a catalyst to lower that activation energy. Okay, so here we see this is the normal reaction without a catalyst added, and here is with a catalyst. So remember, our activation energy is the difference between the reactants and then that complex, so that peak of these graphs. So here, without a catalyst, we have a difference from right here until about right here. That's a pretty big difference. And then with our catalyst, our difference would be from about here up to about right here. So a lower difference. So we're lowering the activation energy, which allows the reaction to get started quicker, which of course increases the rate of the reaction. The activated complex, which is labeled right here, again, this is that same energy diagram we were looking at a few slides ago. This is the structure at the maximum energy point along the reaction path, and it's very unstable. It's kind of like the in-between as we're going from our reactants to our products, and it will typically be about halfway through the reaction. In these kinds of graphs where you see the peak here, that's where your activated complex will be. You will see some graphs without a true defined peak, but the activated complex will go somewhere in the middle. Okay, so right around the middle of the reaction. And then the change in enthalpy, also known as delta H, is the heat that's lost or gained in a chemical reaction. Okay, so your delta H, if we're going to calculate it, would be the enthalpy of the products, okay, so on the right-hand side, minus the enthalpy of the reactants on the left-hand side. Okay, so you can tell if something is endothermic or exothermic either by looking at the potential energy diagram or by calculating it. So if you were given numbers, you would be able to calculate it as well. So if the delta H is positive, then the reaction is endothermic. So the heat of the products are going to be greater than the reactants. And then if delta H is negative, that means the reaction is exothermic and the heat of the reactants are greater than the products. Okay, so if it's positive, so if the difference is positive, that's endothermic, heat was given to the system. Delta H is negative, exothermic, heat was released. Okay. So products tend towards lower energy, a negative delta H. So in a lot of reactions, we're actually going to see that it's exothermic. And they tend towards more randomness, so increased entropy, and that's just a law of nature. That's what happens. So products of exothermic reactions are usually more stable, and they result in lower amounts of heat. Because remember, in an exothermic reaction, we are losing heat, and the heat of our products, or the energy of our products, are lower than the energy of our reactants. Okay. The more negative the delta H, so the bigger the difference between the products and the reactants, the more stable the product is. Okay, and that is it for potential energy diagrams. You guys are going to label 4 diagrams today in your assignment. I'm going to have another video where we go over potential energy diagrams more in depth, and then I'm going to link a YouTube video with a really awesome lady. She does like chemistry review, just like basic chemistry. She does a really good job of going over potential energy diagrams as well. So if you need some additional help with that and just kind of hearing it a different way, I would definitely recommend seeing that video. And again, I'm going to link that in your assignment today. So there'll be a link to a video with my examples, and there'll be a link to the other YouTube video going over potential energy diagrams. But of course, as always, if you're having trouble, let me know and I will be more than happy to hop on Zoom and help you.